So let's look at this limit. For example, number 2, we have a limit as x, y approach 9, 1. Notice the notation because we have two variables here. We have each variable approaching a certain number. So we don't have, we're approaching a point, not approaching a value this time. So, well, if we try direct substitution, let's see what we get. So that's going to be 18 times x, which is 9, times y, which is 1, minus 2 times 9 squared, over 3 times the square root of 9, or 1 rather. That's y, not x, minus root of x, which is root of 9. So this is going to be 9 squared, which is 81, times 2, isn't that 162? And 162 minus 162 over 3 root of 1, which is 3, and root of 9, which is 3, 3 minus 3. Yes, we get the 0 over 0 indeterminate form. All right, well, this is good. Whenever we have a 0 over 0, it means this is good because we can apply pretty much every algebraic technique. So we can simplify or divide out those two factors that are causing trouble in our expression, causing this 0 over 0. And, well, let me erase this part because I might need the space. So let's see. So at first glance, it looks like we can factor out the numerator. So limit. So when I write these limits with more than one variable, instead of writing these order pairs like x, y, going to 9, 1, notice how much space actually consumes here. So I'm going to use an alternative notation. You're more than welcome to use it as well. X approaching 9, y approaching 1. I think it's more compact and it's easier to follow rather than having that long line, because I wouldn't be able to write this tiny, right? And that's, well, what do we have for the numerator? 2x, leaving us with 9y minus x over 3 root of y minus root of x. Well, is there anything we can do to evaluate this limit? Well, of course, this will still be an indeterminate form because we haven't divided out any common factors, in particular those common factors that cause the 0 over 0. Any ideas on how to compute this one? What to do for this one?
Can we do L'Hopital?
L'Hopitals, I wouldn't well, so here is an issue. We might be able to use L'Hopitals, however, we have more than one variable here. So, I mean, we would have to use the topic that is coming in the next section. So, in this case, we would have to use an algebraic technique. Well, we factored out the GCF.
Multiply by the
Conjugate.
The complex conjugate?
The conjugate of the denominator, that's one way. Yes. And that conjugate would be 3 root of y. Okay, let me just write it down. Even though this is correct, that's one way to do it. However, you don't want to FOIL all this, do you?
Oh, no.
Okay. No, you don't want to do it, but it's fine. I mean, it's valid. If you want to do it that way, it's valid. Well, 9y minus x. I'm going to treat that factor as a difference of squares, but wait a minute, it's only the number 9, which is a perfect square, not the y, not the x. However, if we write y as the square root of y squared and x as the square root of x squared, well, we can turn those into perfect squared. In other words, I'm going to write this, let me just rewrite it. Limit to x, that's quantity squared minus quantity squared. Well, in this case, 3 root of y minus root of x. Doesn't that take us back to 9y and x respectively? All right. So I think that's shorter than going with the conjugate. The root of y minus root of x, x approaching 9, y approaching 1. All right. So notice this form. Notice we have the form a squared minus b squared. What's that form? I think it's one of those special products to factor. It's a difference of squares. So limit x approaches 9, y approaching 1 of 2x times, well, basically a minus b, a plus b. So 3 root of y minus root of x, 3 root of y plus root of x. So essentially, we're treating this like a difference of squares in which this is a minus b times a plus b. Whole thing divided by 3 root of y minus root of x. Cancel the factor 3y minus 3 root of y minus root of x, which is in fact those factors that are causing the troublesome 0 over 0. So once we clear those two factors, we're safe. X approaching 9, y approaching 1. That's 2x times 3 root of y plus root of x. And we're good to go and plug in our values. And compute the limit. So that's going to be 2 times x, which is 9, times 3 root of y, which is 1, plus root of 9. And this will be 2 times 9, which is 18, times 3 plus 3, 18 times 6, 108. All right. So that's one example. I mean, basically the same techniques that we used back in Calculus 1 or even in Calculus 2. So, but in this case, we're applying this to functions with more than one variable at the same time. Let's have a look at another limit. Okay, limit x, y goes to the point 1, 2 for the function 5x squared divided by x squared plus y squared. So let's try direct substitution. Hopefully it works. I mean, so that's 5 times 1 squared divided by 1 squared plus y, which in this case is 2 squared. Oh, that's not even a 0 in the denominator, so this is great. 5 over 1 plus 4, that's 5 over 5, and the limit is 1. Yep, so, I mean, just plug in the values where they correspond for the variable. That's it. Let's see if the next limit works. All right. So what is this? So that's 1 over 0 squared plus 0 squared. Wait a minute. No, that's well, that's the form k over 0. And we mentioned in the previous class that whenever we have a constant over 0, that's not an indeterminate form. For now, let's call it d and e. All right, d and e. So for letter C, well, direct substitution, that's 2 squared minus 2 squared, that's 0. Over 2 minus 2, that's 0 over 0, which is great. X approaching 2, y approaching 2. So we can go x minus y, x plus y. And divided by x minus y. Can we cancel this? That's limit x plus y. X approaches 2, y approaches 2. That's 2 plus 2, and yes, indeed, that's 4. Right? Let me go back to letter B. I mean, we're supposed to call this D and E. However, well, what if we look at the function in two different projections? Because essentially, this is z equals to, what is that? 1 over x squared plus y squared. So we can look at the x z traces by setting y equal to 0, and we can look at y z traces by setting x equals to 0. So looking at the traces, okay, x z, we should get z equals to 1 over x squared, and y z traces, that's z equals 1 over y squared. Right? So if we think of this in 3D, well, on the xy plane, what do we have? So it's going to look like, well, number one, individually. So this looks like the graph of y equals to x squared, in which we have the two tails of the graph pointing up to positive infinity. So we can do this in the xy plane and on the yz plane. Well, because this is going to z, actually, we can think of this like a volcano, actually. Right? It's going like this. And in this case, well, notice from every single direction. So as we approach 0 from every direction, what's the z value being hit? Apparently, infinity. All right. I mean, it's still D and E because infinity is something that never ends. There's no limit. But really, the term D and E, we use it whenever we're looking at side limits, and the side limits do not agree. But in this case, I think it's worth looking at, sort of trying to look at the traces of the graph and see what we get. All right, so here is the issue with limits when it comes to functions of multiple variables. So last time we discussed that we can approach a value not just from the left, not just from the right, like in functions of single variable, like back in calculus 1 and calculus 2. In this case, you can approach a value from pretty much your favorite direction, from the left, from the right, from the top, from the bottom, diagonally. I don't know, like a wave, and then approach a wave on one side, away from the other side. So there's pretty much infinitely many ways to compute a limit. The issue with limits is the fact that if we look at different paths, that's what we are going to do, consider different paths. We may get different limits. So the minute we get different limits, well, we just call it a D and E. So, and on the other hand, if we start getting the same limit, we still cannot conclude that the limit exists at that value because, well, again, because there's infinitely many ways, we cannot, just showing 3 examples does not prove that the limit is indeed whatever that number is. However, it proved that the limit is D and E the minute we get different values. So this is what we're going to do for this limit. So number one, let's try direct substitution. That's 0 squared minus 0 squared over 0 squared plus 0 squared, quantity squared. Well, this is essentially 0 over 0. All right? So, what do we mean by different paths? Well, so the number one path that we're going to explore here is number one, path when x equals to 0. Right? So when we set x equals to 0, we will remain, or our limit will remain only in terms of y. So it will become a single variable limit. So that's limit as y approaches 0, no longer x equals 0, or no longer x approaching 0 and y equals 0, just y approaching 0. So that's 0 squared minus y squared over 0 squared plus y squared, quantity squared. All right, so this will be the following. Limit negative y squared over y squared as y approaches 0 squared. But what's y squared over y squared? Isn't it negative 1? And y approaches 0. And negative 1 squared, that's 1. Right? So that's the limit if we set x equals to 0. Let's see what happens if y, for number 2, for the second path, whenever the path y equals to 0 and limit, so when we set our y's equal to 0, our limit becomes another one single variable limit, but this time in terms of x. X squared minus 0 squared, x squared plus y squared, quantity squared. Well, in this case, limit, that's x squared over x squared as x approaches 1. And well, these x squareds cancel, leaving us with 1 squared. X equals to, the limit equals to 1. Well, so for now, both limits look the same. But that doesn't prove anything because there's many other paths that we can consider here. Again, just these two examples are not sufficient, evidence to say, oh, the limit is going to be 1 because on both cases it coincides, right? So let's try another path. What about along the path y equals to 2x, all right? So we are going to approach the origin, in this case, along the line y equals to 2x in a diagonal line, all right? Recall that we can, on a surface in 3 dimensions, we can approach a value from the left, from the right, from the top, from the bottom, diagonally in accordance with one equation, diagonally in accordance with another equation, infinitely many possibilities. So what are we going to do here? These y's will get replaced with 2x right here. So this will be limit x approaches 0, that's x squared minus y, which in this case is 2x, quantity squared over x squared plus y squared, which in this case is 2x, quantity squared. And the whole thing quantity squared. So let's see. So x squared minus 4x squared, x squared plus 4x squared. X approaches 0. And well, we can combine like terms both in the numerator and the denominator, and so this will be x squared minus 4x, that's limit negative 3x squared, quantity squared over 5x squared as x approaches 0. And we can divide out the x squares, and this will be negative 3/5 squared, which is 9 over 25. So this is one counter example in which using a particular path no longer coincides with the other limits. All right? Conclusion then. Conclusion. D and E. The limit does not exist.
Yes. So for the path 3, can you use any equation of a line?
A half
Like, could I just do y equals x?
y equals x. y equals 7x, y equals, just be careful on the path, and we're going to discuss in a later example, in some cases certain paths may not be used. So like, yeah, just said 1/2 x, right? That's fine. 1/2 x is a good example. So let's look at the next one. Oh, that's actually the next example. So let's show that the limit does not exist by considering two paths. So in this case, we are not coming up with random paths. We are going. They're giving us a path. Yes.
For that last question, we're concluding that the limit doesn't exist.
Does not exist. Yes, because for at least one path, we're getting a different value than the other ones. Okay. So let's show that the limit does not exist, and actually they're telling us that it does not exist. So we don't need to do this. What's it called? The replacement theorem here. So let's do the first part. Let's go and substitute. So number one path. That's y equals to x. What are we going to do in this case? Well, wherever you see the y's, replace with x's. So that's limit of negative x times quantity squared, y quantity squared, divided by x squared plus quantity to the fourth. What is that quantity that we square and raise to the fourth respectively? Well, x. All right. And in this case, because we are replacing y with some expression, the two variable limit becomes a single variable limit. In this case, x equals to 0. So let's simplify this. X to the second, well, that's x squared times x. That's negative x cubed. And then x squared plus x to the fourth, that's just x squared plus x to the fourth. And limit as x approaches 0. All right. Well, so there's a couple of things that we can do about this limit. I mean, we can factor out x squared from the denominator and then divide out x cubed over x, but we can go with the shortcuts from calculus 1 or from pre-calculus, which actually, well, no, you know what, we can't do that because we're not at limits at infinity. Never mind. So we will have to do the algebra. X cubed, and that's x squared over 1 plus x squared. All right. X approaches 0, and well, limit negative x over 1 plus x squared as x approaching 0, so that's negative 0 over 1 plus 0 squared, that's 0. So that's the result going through the path y equals to x. All right. Let's discuss the second path. And for the second path, they're asking us to replace x with y squared. So every instance of x, replace with y squared. So limit, and well, when we replace x with something, the limit becomes in terms of y. This time y equals to 0, so that's x times y squared divided by x squared plus y squared. But notice I left parentheses open for the expression that we will replace x with. In this case, y squared and y squared. All right. So let's see. Simplifying this, we're going to get limit. That's y approaches 0. That's y to the fourth over y to the fourth. And this is supposed to be to the fourth. That is limit y to the fourth over 2 y to the fourth. As y approaches 0, well, we can divide out the y to the fourths. That's a limit. Oh, that's actually, well, we can just go all the way to 1/2. Or rather, oh, I'm missing a negative. Yep, negative. negative 1/2. And well, this proves that the limit exists. However, if we were getting the same limit over and over, that doesn't prove that the limit exists, because there could be, some paths for which the limit can be different that we are not exploring. Now, the question is, and that's the bottom part for this exercise. Well, let's explain why the path y equals cosine is not an appropriate path. However, on the other hand, the path y equals sine x is an appropriate path. Recording again. So, in this case, we're trying to approach the point 0, 0. All right? Is the point 0, 0 on the graph of cosine? Because when x equals 0, cosine is 1. All right? And what about for sine? 0, 0 exists on that graph. So that's why sine is an appropriate, but cosine is not. Now, coming back to Kyle's question. So, can you just choose your favorite path? Well, so Kyle mentioned, let's call it 4. Path y equals to 1/2 x. Well, we want to approach the point 0, 0. Is the point 0, 0 on the graph of y equals 1/2 x? Yes, right? So that's why this is appropriate. How about 7x? How about 7x plus 3? No, it's not anymore, right? So that's why we cannot just choose our favorite. I mean, we may get different limits, yes, but for this reason, because this point we want to approach to doesn't pass through the graph of the path that we want, well, that's why it's not going to be an appropriate path. All right, let's talk about continuity. Well, so continuity for a function, well, we want to make sure that the limit exists and also the function is defined. So, well, I'm not going to go back to my calculus 1 graph. I think I have enough space to draw a mini graph, so you might want to use the back side of your paper. I'm going to use my blank space here. So we have this example here, and I have this, and I have this graph. And well, no, that's not the one. So number 1. So this represents f of x. All right, from Calc 1, just f of x, just a single variable function. And again, the idea is that the limit will exist as long as the limit is exactly the same when we approach from either side. And in this case, well, let's whatever L is, L and X. Okay. So limit exists. However, the question is a function defined at that point? No. But f of x undefined, all right? It's undefined. Now, what if I had this point in the middle of nowhere? Is the function still undefined? Not anymore, right? I mean, it's defined about that. It's defined at that point in the middle of nowhere. But the thing is, the function it's still not continuous, because again, the definition for continuity is that I can draw the graph of a function without ever having to lift the pencil. And in fact, because of this hole, I have to jump to continue my way here, right? So even if the function is defined somewhere else, well, and here is the thing. So the fact that a function is defined does not necessarily imply that the limit of the function at that value exists. However, the converse states that if the limit exists and if the function are both defined, well, the function is continuous in this case. So let's have The theorem from back in Calc 1 was essentially that limit of f of x as x approaches a has to be exactly f of a, right? In order to have a continuous function. Well, so what do we have to do for multivariable functions? Well, let's just add one more letter. And instead of approaching a value, we're approaching a point. And the output will be, well, whatever f of a be, you know? So, and well, again, for when we study continuity, what we're essentially doing is finding the domain of a function and we're rephrasing it. So yes, the domain of the function is boom boom this for all real numbers, or except this or that value. But now we're going to phrase it as the function is continuous within these intervals, which happen to be the same intervals that are the domain of the function. So let's have a look. And well, again, we're going to use the same guidelines as in intermediate algebra, college algebra, to find the domains and to get the continuity. So we have a cosine function. Well, we know that the function cosine is defined for every real number. All right, so cosine. The cosine function, well, we don't have any issues with the cosine function itself, you know. It doesn't have any holes, any asymptotes, any jump discontinuities. However, we would have to look at the angle, you know, the quantity inside of the parentheses of the cosine function. Well, what do we have? A rational function. So we want to make sure that the denominator is not 0. However, let's think about x squared plus 1. Is x squared plus 1 ever 0? No. So continuous everywhere, isn't it? Continuous for all x in the real numbers, right? Or actually for all order pairs x, y in the real numbers. This upside down a means for all, and this sort of e means belongs to, you know, or in the set of real numbers. What about letter B? So the exponential function, we don't have any issues with it, right? However, if we look at what we have in the exponent, we have an x in the denominator. That's some trouble, right? So we can say it's continuous for all x, y in the real numbers, except x cannot be 0, right? That's the only condition, as long as it's not, as x is not 0. Otherwise, we're good with this function. And for letter C, we have this piecewise defined function. Well, what is the analogous to this kind of piecewise function? So you might have seen, from intermediate algebra, whenever you have the graph of something like this and something like this. Does that graph look like a continuous function? No, it doesn't, right? Because they're not connected. How about this one? Continuous? All right? So in this case, in this situation, limit of f of x, you know, from either side, as x approaches, let's say c, is equal to f evaluated at c. It's the function is defined and the limit matches the value of the function. Well, in that case, that means that I don't have to lift my pencil at all, right? And then, okay, let me draw the other example. So in this case, to begin with, oh wait, no, this is fine, this is fine. Let me something like this. Number one, limit f of x as x approaches the value of c again. Well, let's look at the limits on either side. The limit exists because we're getting to the same value, to the same point. Alright, however, is the limit of f of x equal to the function evaluated at that value? No. So in this case, this fails to meet the condition for continuity. So we're going to do something similar with the function, with the piecewise defined function that we have for letter C. Alright, so in this case, in order to determine whether this function is continuous, we need to make sure that limit x approaches 0, y approaches 0, and of f of x, y equals to f, or rather, f of x, y, why not? F of 0 evaluated at 0. We need to make sure those two quantities are the same. So we're going to do one calculation at a time. So, number one, the easiest one. Let's evaluate the function. What is f of 0, 0? Well, so in this case, we have this ugly looking expression with the condition that we cannot plug in the point 0, 0. However, the other condition here states that whenever x and y are exactly equal to 0, the value of the function is 1. Alright? So that's number one. Number two, we need to check the limit. And again, for the limit, yes, even though for limits we plug in values which looks exactly the same as evaluating a function, the concept behind the limit is not evaluating a function, is how close we get, which value do we get as we approach certain value, but the mechanics are pretty much the same. So limit x approaches 0, y approaches 0, 4x to the 4th minus y to the 4th over 2x squared plus y squared. I think we're going to have the 0 over 0 indeterminate form, right? This means we're good. Okay, so that means we can do algebra here. And any ideas on what to do here?
Factor the top.
Factor the top difference of squares. X approaches 0, y approaches 0, 2x squared minus y squared times 2x squared plus y squared. 2x squared plus y squared. Oh, this one goes away. Precisely those factors that cause trouble over here, right? So this means limit 2x squared minus y squared, x approaching 0, y approaching 0. So that's 2 times, well actually, how about just 0? Alright? I think it's clear that it's going to be 0. Now, let's compare. Is the value of the limit the same as the value of the function? No. Continuous or discontinuous? Discontinuous. So, we need to state discontinuous. Or actually continuous for all x, y in the real numbers except at the point 0, 0. It's not continuous at that point. Right?